The first thing I defined was a discriminant. We don't really need to know what it is here, but in general, if we have an elliptic curve, say E, given by y squared equals x cubed plus ax plus b, to ensure a non-singularity, that the curve is always smooth, we just say that the discriminant given by 4a cubed plus 27b squared is non-zero. So we just have to remember this relation here. But yeah, that's just to make sure that there's no singularity. So I want to first state what the Nagell-Lutz theorem is. So given an elliptic curve of this form E given by y squared equals x cubed plus ax plus b with a non-zero discriminant, we let a point P be on the elliptic curve over the rationals, and then we write P to be x comma y, so we can assume it's not the identity. Then we say that this point P has rational order if, well, sorry, this rational point P has finite order if it has finite order, then, so if order of P was less than infinity, then this means that both x and y are integers, and either y equals 0 or y divides the discriminant given by 4a cubed plus 27b squared. So this theorem gives us kind of a way to test whether a point is infinite. And it also gives us a way to find all the finite points, although that does still require a little bit of calculation. So note that what we're saying is that a point P is finite. Sorry, a point P is infinite implies integer coordinates and a condition on y here. And this should be a y squared, sorry. So y squared divides the discriminant. So let's consider a couple of examples before I prove the actual thing. So consider the curve E given by y squared b minus x plus 1. So A is -1 and B is 1. So this means the discriminant is 23. So if we look at the statement of Nagell-Lutz, we want to try and find all points of finite order on this curve. So that means all finite points have to have one of these conditions. Well, it has to satisfy all these conditions. It might not be finite if it does satisfy all of them, as we'll find out later. But so first of all, we want E to be on E over the rationals such that E equals x comma y, and both x and y are integers. And we also have the constraints of y. So if y equals 0, sorry, let's do something else here. So the possibilities for y is 0 given there, and also when y squared divides the discriminant, but 23 is prime, so y can only be plus or minus 1. So we only have 3 possibilities for y. And then to find all points of finite order on this curve, we just figure out if there are any corresponding x's, and actually we have the points. So if y equals 0, then we have the point 0, well, sorry. If we solve this, 0 equals x cubed minus x plus 1, there are no integer solutions. All of them are either rational or complex. So we can discard the case y equals 0, and we're left with y equals plus or minus 1. So we have the points. If we solve y squared So if we solve 1 equals x cubed minus x plus 1, then we get x cubed minus x equals 0, and we get the points 1 comma plus or minus 1, negative 1 comma plus or minus 1, and 0 comma plus or minus 1. So we've got, note that I write the plus or minus 1 here because, well, it doesn't really matter what y is, whether it's positive or negative, because it's symmetric across the x-axis anyway. So 0, 1 is the inverse of 0, negative 1, and if a point P has a finite order, then its inverse has finite order as well. So we only have to check one of them. So the first thing I'm gonna check is the point 1, 1. And actually, if you compute, say, twice 1, 1, we get negative 1 comma 1. And if we compute 3 times 1, 1, we get 0, negative 1. And so that means actually 1, 1 gives us its inverse. It gives us this point and its inverse, and it also gives us this point and its inverse. So this would be, so say this 1, 1 is P, then this would be P negative P. This would be plus or minus 2P here, and this is plus or minus 3P. So that means we only need to show whether P, our original point 1, 1, has finite order or infinite order. And actually it is infinite order, because if we calculate 6 times 1, 1, we get a quarter 7 over 8. And if we look back at the statement of Nagell-Lutz, it says that a point has finite order, then it has integer coordinates. So that means if it doesn't have integer coordinates, then it's an infinite point. And here we see that 6 times 1, 1 has a rational coordinates. It doesn't have integer coordinates. So that means 6 times 1, 1 is has infinite order. And then yeah, so this has infinite order. So that means 1, 1 has infinite order, and so does twice 1, 1, 3 times 1, 1. So that means every point, all 6 of these points here, have infinite order. So that means if we go back to our original curve here, this curve only has one point of finite order, namely the origin, the point at infinity, the identity. Right. So what's the time? I think I have time for one extra example, just really quickly. So let's consider, I'm going to skip example 1.3, go straight to example 1.4. Consider this elliptic curve. Then the discriminant is 112, which is 2 to the 4 times 7. That's a typo in the notes. And then that means the possibilities of y. Recall that a point of finite order on E, the y coordinate has to, the y coordinate squared has to divide D or be 0. So that means y has to be either 0 or a square dividing this. So obviously 1 is in there, and it can also be 2, since 4 divides 112, and 16 also divides 112. So plus or minus, y could also be plus or minus 4. So here we have 7 cases to check. And if we solve for integer values of x, I just put the elliptic curve into Wolfram alpha and solved it there. We get the only integer points with y equal one of these are 1 comma plus or minus 2 and negative 1 comma 0. So we only have to see whether these are the only kind of candidates for finite points. And then clearly, since the second coordinate of this one is 0, then this has order 2, so it's finite. And then we can also check this one has order 4 just by multiplying it by 4, and so it has finite order as well. So So Nagell-Lutz gives us these 3 points plus the origin are the points of finite order on this elliptic curve here. So as you can see, the theorem gives us a nice kind of way to figure out the points of finite order on elliptic curves, and it also it also helps with a lot of things down the road later on. So now I would like to prove the theorem. So this proof uses kind of the idea of the p-adic valuation. If you can't remember the p-adic valuation for some prime p, so a prime p, then the p-adic valuation is given by Vp of A so the p-adic valuation of some A in the rationals except 0. Vp of A is kind of the largest or the smallest power of P dividing A. So the proper way to write it, if you recall a neat theorem of p-adic numbers, is that for a p-adic number A, we can actually write it in this form: m over n times p to the v, where m, n, and p are all integers and they're all pairwise coprime. And actually, this v is our p-adic valuation. So, for example, the p-adic valuation of 4 in the 2-adics, well, this is 2 squared, so the p-adic valuation would be 2. If we had, say, v2 of 12, then this would be also 2, since 12 is equal to 2 squared times 3. So m would be 3, n would be 1, and v would be 2. And then we can also do it the other way. So v2 of a quarter would be -2, and so on and so forth. So that's the idea of a p-adic valuation. And as we shall see later, this kind of is a way we can give a proof of the Nagell-Lutz theorem. Just a bit of notation that would help later on. I want to define Rp to be the set A on the rational every rational number that satisfies this condition that its valuation is positive. So this is the set of all rational numbers with denominator coprime to P, basically. And you can also show that this is a ring, a subring of the rationals quite easily. The next definition I want to, the next thing I want to define is this object here. So E of P to the V, I don't think it actually has a name or anything. It's just something we use in the proof. And we call this set the points on an elliptic curve Q, elliptic curve E, which we've defined, such that the valuation of the x-coordinate is less than -2v, where v is given in this power, and the valuation of y is less than -3v. And then we also add the point at infinity onto that. So this set is given by every point with valuations less than kind of a particular number. And why we do this? Well, I'm going to prove a little lemma so we know why we should define the set and how it's going to help us give a proof. So the lemma 2.4 states, let a point be in the rational points of an elliptic curve, and write the valuation for some prime p, it could be any prime, of x to be -I, and the valuation of y to be -j. And we let I and j be positive integers. So I comma j greater or equal to 0, and also in the integers, so in the natural numbers and 0, I guess you could say. So the lemma says that x comma y is in EPV. Recall this set here up here for some v, and then the proof is quite simple. So if the valuation of x is negative I, then we can write x to be some x prime over p to the I. And we can write y to be y prime over some over p to the j, and then x prime and y prime are units in the p-adix. So that just means that when you write it out, it doesn't have any, the valuations of x prime and y prime are both trivial. So then we can just do the straight calculation. Y prime squared over p to the 2j is x prime cubed plus p to the 2i ax prime plus p to the 3i b over p to the 3i. Recall that our elliptic curve E is given by x cubed plus a x cubed plus ax plus b. So that means when we just substitute these in, we get this thing here. And this, we can see that since y prime was a unit in the p-adix, then the numerator on this side is a unit, and the numerator on this side here is also a unit. So that means the valuation of both sides must be equal. In particular, 3i equals to 2j. So this tells us that if we have a point x comma y, then the valuations actually have kind of some constraint on them given by this relationship here. And actually the part where v comes in, we can just explicitly write a value for v. This v, we can actually get this v from here. I think it's something like v is twice I. So this lemma shows that a point with non-integer coordinates exists in one of these objects. Later on, we want to show that these are actually subgroups, and that's what basically the bulk of the proof is, showing that this set E of p to the v is a subgroup of E of q of the rational points over the elliptic curve. And if we think about it, a point in here kind of has some denominator. So x would be equal to some x prime over p to the something up here, p to the, what did I write? P to the I, and y would be some y prime over p to the j. And that means kind of the denominator, if we let this v get larger and larger, then the denominators kind of get larger and larger. And then if we look at the, if you know anything about kind of the p-adic topology or something, I don't know much about it, but the points kind of get bigger and bigger. They get closer to the point at infinity, so to speak. And then that means they don't actually kind of, they never go back to the original point, that they do not lie inside, say, they don't lie inside the point, the integer points on the curve. So that's some motivation of what we're doing, and that's the first result we need to get into the actual proof. So yeah, so most of the proof is trying to show that E of p to the v for every p and for every v is a subgroup. the next thing we need to do is to, so if we think about the point of infinity, that's at infinity, we kind of want to birationally move it to the origin, and that makes everything a lot nicer. I mean, you could do everything with the point at infinity, but that would just be a pain. So recall we have this elliptic curve here, and we want to define a cubic equation. So this is an elliptic curve, isn't an elliptic curve. So s equals t cubed plus a plus s squared plus b s cubed. And if we take the map phi from the rational points of E to the rational points of the second curve, then this is given by, say, phi of x comma y goes to t comma s, where t and s are given by x upon y comma 1 over y. And in the case of the point at infinity, we also define phi of infinity to go to 0 comma 0. And then phi of any point of order 2 goes to kind of infinity on the second curve. Then what I claim is that this curve is a birational thing and a birational map, and the kind of group addition is preserved before and after phi. So basically, after we prove this, we can say that anything that happens here, except if we kind of throw away the points of order 2, then it also happens here and vice versa. So we can actually just prove things over the curve C, and we get a result over the curve E. The proof of this is straightforward. Clearly, this thing does give a birational map. It works out just by plugging these in and rearranging, and we also get the inverse map where we set y equals 1 over s and x be t over s. And it's also quite straightforward to see that if 3 points are on a straight line, then phi maps those 3 points to the same straight line. So that means that phi of a line is also a line. So if you think about that, that means when we take, if we take 2 points P and Q inside the rational points of E, then phi of P plus Q is equal to phi of P, phi of Q. Where, although you have to note that on this side addition, we take it over the point of infinity. So that means when we take negatives, we flip it over the x-axis. But here the identity is the origin. So that means we have to flip it over the origin point. So on the left-hand side, if a point was up here, then negative P would be somewhere down there. And on this side, if P was here, then negative P would be there. And if you look at Silverman and Tate, there's kind of a cool picture that shows you how the map actually works, but I'm bad at drawing, so I won't try and draw that out. So in a similar fashion, recall that we've defined the set E of P to the V. So I also want to define definition 2.6, define C of E to the V to be the set P of S inside the rational points of C, given by valuation of T is greater than V, greater and or equal to V, and the valuation of S to be greater than or equal to 3V. And why we define it like that? Well, lemma 2.7 tells us that phi of the thing is equal to. So that means to show that the thing is a group, we only need to show that the thing is a group since phi is birational, so it goes both ways. And it's not too hard to prove. It's like 1 line long or 2 lines because my handwriting is really bad. So if you let well, recall that this is we have a constraint on the valuation of x and y, so we can write proof. We can write x to be m over n p squared v plus I, and we can write y to be sum u over w p to the 3 p plus I, where u, w, m, and n are all integers and they're all co-prime to p, or units in the p-adics, however you want to put it. And well, I is greater than or equal to 0 for some, well, yeah, it's for some I, because recall that I don't think I still have it. Oh, I have it here. Recall that this is an inequality, so that's why we have the I there. Then we simply get t is x over y, mw over nu. This thing is a unit, p to the v plus I, and s equals w over u. The thing is a unit, p to the 3 of v plus I. So that means this thing corresponds to this condition up here, and the thing corresponds to this condition here. So everything works out. So we've proved lemma 2.7. Now for the big proof, lemma 2.8. Lemma 2.8. This is kind of a big lemma, but the proof also isn't too hard, it's just tedious. So C of PV is a subgroup of the rational points of the cubic equation C. Well, I am lazy. I'm not going to prove this in full. But look at Silverman and Tate. I think I wrote pages 51 to 53 for food details, but I'll sketch it here. And all the gaps are basically just computational details. You just have to expand a couple of polynomials and just compare terms and stuff like that. But to prove a subgroup, all we basically need to do, since the thing is already a group, we just have to prove closure over addition and also over negation. So if proof, let P1 be given by T1 comma S1 and P2 be given by T2 comma S2. And first of all, suppose these are distinct points. That means, yeah, so that means we aren't doubling the points yet. Then we consider cases if the x coordinates are the same. Sorry, the t coordinates, the first coordinates. T1 equals T2. Then the third point of intersection will be over C would be some point P3, but T1 is fixed since this is a vertical line, and F3 is something else. And then that means P1 plus P2. So since this is the third point of intersection, we, if you remember the group law, we need to also get the third point of intersection between P3 and the identity point. The identity is 0, 0, so that means taking negative of, it will be negative P3, which is just negative both coordinates, since we're flipping it over negative T1 minus. Oh, hi, Euron. It will be the thing here, and okay, yep. So P P1 plus P2 is indeed a point inside of C of P to the V, because well, this thing we already have a constraint on because T, we assume that these points themselves are inside C of P to the V, and any point on the elliptic curve, if the first thing has a constraint, then the second thing has a constraint over the p-adix. So that's the case T1 equals T2. So now we suppose T1 not equal to T2. And then, well, the way we do this is kind of a lot of messy stuff. So we take the line between the 2 points P1 and P2 given by just the line equation, and alpha is the slope, so it's S2 minus S1 upon T2 minus T1. So that's the line between P1 and P2. Then also, if we kind of look at the equations for C, recall that C was just a cubic. So if we had S1 and S2 on one, well, we have S on one side of the cubic and we have all the T's on the other side, so we can easily just find S1 minus S2, and that's just T1 squared minus T2 cubed plus A times T1 minus T2 S2 squared, blah, blah, blah. And this is where I'm gonna wave my hands a bit, because well, if you see, we have kind of, well, we have an S1 minus S2 here, we have T1 minus T2s here, and we can kind of group everything onto one side and then equate it with this thing here. So in fact, we get alpha equals, well, we had the original thing, right? And you can verify this for yourself. It's something on the top divided by 1 plus something else on the bottom here. And a similar thing, you can also do a similar thing in the case of doubling. Again, I'm not going to do it here since it's just overly tedious and we still have a lot to go through. But when you do the calculation, you find that these two things here, they will be units inside our field, our subgroup RP, subring I should say, RP, and that means that kind of, well, there will be units. Sorry, the denominator will be a unit. So that means because we have a 1 here, and yeah, this will be a unit because the thing we'll find is inside, say, P to the 2V of R of P. So that means alpha itself is in the thing here. That's a typo in the notes again. So yeah, this is where I've waved my hands. Just look at Silverman and Tate for full details. But then kind of, if you just follow through and let P3 again be the kind of the third point of intersection, so not the sum, but the negative sum. So this is equal to minus P1 plus P2. P3 is the intersection between L and C, and then if you kind of substitute everything together and hand wave a little more, you would find that we get an equation for T1 plus T2 plus T3, and then that means we can get T. So we'll find that T1 plus T2 plus T3 itself is in this here, and since T1 and T2 are both in P to the V of RP, that means T3 is in the thing as well. And that means we also have a constraint of on S3, and this just tells us that P3, oh, that's not the P. So hence, after a lot of hand waving, P3 and negative P3 are in C of P to the V. And that means it's closed under addition and take negatives, and hence the thing here is a subgroup of the rational points on C. So, well, that was kind of the longest part of the proof, and everything else kind of just falls out. I mean, there's still one more technical result we need. So, clear everything again. So lemma 2.9, so we define a map from the thing E of P to the V over E of P to the 3V. So note that this is over our original elliptic curve, not our thing that we've transformed the one after birational transformation. And then we map this to P to the V RP times over modeled out the thing given by a point on the side, say P maps to T of P, which is x over y. Note that the T is kind of, well, it's the first thing we apply is our birational transformation to move it over to our second curve C, and then we compose it with the projection onto the T coordinate, to the first coordinate. Then we claim that this map here, well, we get this result, T of P1 plus P2 is for any P1 and P2 in E of P to the V, and this is over, so we mod out by the thing on the bottom. This is, how did I do that? I did not know you can do that. Right, so so this is our first result, and then the second result says that T is an injective homomorphism. And this kind of gives us a way to prove the whole thing in the end. So again, I'm just going to speak this proof. I think I'm not going to write anything. So if you recall from the previous theorem, then if we have 2 points, P1 and P2, then inside E of P to the V, then, well, okay, I lied. I'm going to write something. Then we know that T of P1 plus T of P2 minus this thing. This is almost 0, not quite 0. It's inside the thing here. And that means if we just mod out by this thing, we get the homomorphism. It's injective as well by some theorem from algebra. I can't remember what it's called. And because the kernel of the map would be the thing here, and then we mod out by the thing on the left hand, this thing on the left hand side before kind of applying this phi here, and then we take E instead because that's before a transformation, and then this gives us injectivity. I think that's actually a typo in the notes. The C of P to the 3V in the notes should be an E. But yeah, so that's kind of the last lemma we need before we actually start proving the theorem at hand. So theorem 2.10. a point of finite order has integer coordinates. And this itself looks like the Nagell-Lutz theorem again. Also, well, it's the first part of it. What did I do? Proof. So we consider cases here. But so we suppose a point P. Sorry. We suppose point P has finite order. So let's call that order M. And suppose for a contradiction that we don't have the conclusion, suppose that suppose for contradiction. Either x is not an integer or y is not an integer. Then there exists some prime P such that the denominator kind of divides, the denominator divides P, otherwise it wouldn't be, it would itself, this is not in, the number would be a rational number, so that means there has to be something in the denominator. So there's some P with...
Maybe you want to call Q, Tristan. Well, P is already reserved for your point, no?
Oh, yeah, my bad. Thanks, Jeroen. Yeah, so assume there's some prime Q and some integer v greater than 1 such that our point P is inside Q to the v, but it's not inside the next one. And also, it's quite easy to see that this thing, so we get inclusion of so this thing is contained inside the thing. So note that which way do the inclusion signs how it goes. The thing on the right is. So note that we have something like this and so on and so forth. So anyways, where was I? So yeah, so we have some Q and some V such that these two conditions hold. And actually concretely we can calculate such a V. It's actually the valuation of x times -12. And I think you need to round it somewhere if round it up. And if P, so we consider two cases. We consider the first case, P does not divide M. So case 1, if P does not divide M, then we can, sorry, this should be a Q, not a P. If our prime number Q doesn't divide M, then T of MP, remember T was our map, is congruent to the thing here, mod our thing in our map again. So that was, I think, Q to the 3V R of Q. But then since the thing, M of P is the identity, since P had order M, then that means 0 is congruent to the thing here, but M is not 0, so it means 0 is congruent the thing T of P mod the thing. And then this gives us a contradiction, actually, because if this were to be true, then we'll get P to be inside e to the q of 3v. But then e to the q of 3v, that's contained inside every smaller one. And we get a contradiction. Since we assumed it doesn't lie in the thing, but since 3v is greater than v plus 1, that's a contradiction. And in the second case, if q does divide m, then we do something similar. We get actually the same contradiction, except there's an extra step involved. So we define a second point p prime to be this thing here, m over qp, and here the order of p prime, it's very easy to see that it is q. And then we also have that p prime is in this thing here, and it's not in the next thing. Since it was true for p, then it's also true for p prime. And that's true for some v. And as before, this means that 0 is the thing here, t of q p prime, which is congruent to qt of p prime mod our thingy again, q of and then this follows that well, since q is non-zero again, so this thing is 0, and that gives us a contradiction because we get that p prime is inside e of 3 v minus 1, and that contradicts because 3v minus 1 is greater than v plus 1, and the thing is contained inside. Then it contradicts. Sorry, this should be not contained in. It is actually contained inside that, and that gives us our contradiction. So in both cases, we arrive at a contradiction, and hence our original assumption that x and y are both irrational, not irrational, both neither of them are both integers. That contradicts that, so that means they both have to have the point has to have integer coordinates in both. So that's the proof of the first part of Nagell-Lutz. And then recall the second part. We had that if p was a point of finite order, then we had that both coordinates were integer. We've already proved that. The second part was that the second coordinate is either 0 or the square of it divides the discriminant. And that's the next theorem here, 2.11. If p was this thing here, if this was a non-identity point of finite order, as finite order, and this is a point on our elliptic curve E, then we already have that both things are integers. Then we have y squared divides d, or y equals 0. The proof is not that hard. So we can first we have to assume y to be not 0, because we don't want the order of p to be 2. If you recall that the map, the birational map falls down for points with 0 in the second coordinate, because that's a point of order 2, and that maps to infinity inside our transformation by our transformed curve C. So if y is non-zero, then p, the order of p, say it's m, it's greater than 2. And then we can also write 2p to be some x prime, y prime, and this is not the identity by assumption. Then 2p also has finite order, and it also has integer coordinates by our previous theorem. Then if we recall the addition formulas, we have lambda is 3x plus a over 2y, and we have that x prime equals lambda squared minus 2x. And because, well, x was an integer, y was an integer, so is x prime and y prime. And a is also an integer. That means lambda here is an integer, and that means since this is an integer, then that means 2y must divide 3x plus a, or in particular, y must divide 3x plus a. And then from before, we also had, well, we clearly have this thing. Actually, we have equality on both sides, but we only need that. So both of these put together, and noting this identity here that I just copied from Stephen's notes, but you can easily verify that this actually holds, this equality holds. And then note that we have x cubed plus ax plus b on this side. Sorry, it's the thing, and then we also have 3x squared plus a squared. So that means y squared divides the thing, y squared divides the thing, so y squared divides d. And we are done on that end, and I don't know how that happens. So basically, that's the case where y is non-zero, and then the other case y is 0, then that obviously has that's obviously a point of order 2, and that also has finite order, so we're done there. So if the point has order 2, then it's in this case, otherwise it's in this case. And yeah, that's the proof of Nagell-Lutz. So we've proved that any point of finite order, if a point has finite order, then it has integer coordinates, and it satisfies the second coordinate y either is 0 or y squared divides d. So that's the proof. I had a quick afterword as well. There's a deep theorem by however you pronounce this name, Mazur, I think, that says that actually the order of finite rational points of an elliptic curve is at most 12. So it can be any number between 1 and 12, but it can't be 11. And that means using Nagell-Lutz, we only have to check kind of for every point satisfying our conditions. So recall that y has some constraints on it. So we only have to check a finite number of cases, because by Mazur, we only have to check up to n equals 12. And that's why this theorem is quite powerful. And yep, that's my presentation. Thanks. The references I used, I followed Silverman and Tate, and also Stephen's 714 notes.
Thanks very much, Tristan.
Any questions?
I put you a PDF in the chat, which has a nice proof that there is no group of order 11.
Oh, neat. All right. Yeah. Thanks, Lucas.